proof that it's streaming, and then we can go from there. But again, thank you so much for coming on here. We're looking forward to it. And
proof that it's
okay,
streaming.
there we go. There we go. Okay.
There.
All right. So welcome aboard to our fun little podcast called Space Weather Unplugged. And then today we have a special guest, Dr. Mathew Owens from the University of, is it Reading?
It is Reading, yeah.
Okay. I want to make sure I say it right. But he's a professor of space physics over there and one of the people behind the HUXt model that we love to use as aurora chasers. And that stands for Heliospheric Upwind Extrapolation with Time Dependence.
Yes, catchy title.
Which that's the first time I ever said that whole thing out loud. So it's quite a mouthful.
Really.
But it should be fun. I'm looking forward to seeing how, the inner workings of this and how, what it can be used for and what maybe it shouldn't be used for. And yeah, so thank you again. And I will hand it over and we can just roll into it.
Thanks very much. Yeah, thanks
Yes.
for having me. Yeah, so I'll tell you a bit about the HUXt model, a bit of a look behind the curtain, as it were, how it really works. I'm hoping you'll still want to use it after you've seen the dirty secrets that I'll air shortly. So what it's useful for is for forecasting a couple of days ahead. Now, if you're forecasting a couple of days ahead, you tend to have quite a bit of uncertainty in those forecasts. If you want to know what the aurora is going to be like in the next half an hour, you don't want to use this kind of model. You want to go and look at what the solar wind's actually doing, because we have monitors that can see the solar wind that's going to hit the Earth in half an hour's time. But if you want to do some more long-term planning, this is the kind of modeling and forecasting that you have to resort to. So there's a group of us at Reading. There's some names down there that have contributed different bits and pieces. So thanks to all those people too. So apologies in advance if I'm a little bit patronizing at times. I'm envisioning quite a broad spectrum of knowledge about space physics and space weather and that sort of thing. So I'll very briefly introduce the idea that if you want to predict big storms and big auroral shows, what the game is to predict when a coronal mass ejection will arrive at Earth. Now, that coronal mass ejection may or may not trigger aurora, but that's the first step. And so to do that, we need to understand a bit about the solar wind. So I'm going to sneak a little bit of physics in there about what the solar wind is, how and why we model it, and then I'll strip all that physics back away and talk about HUXt, which is a reduced physics model, and I'll talk about why you would want to throw away useful knowledge, because it enables you to do things that you can't do otherwise. And I'll show a couple of forecasts, and I'll sort of talk you through how to interpret them. At the end, I'll talk about some things that are kind of coming through the system at the moment, sort of future developments, but I probably will have run out of time by that point, so I'll skim over those. But I'd really like to get some input from the sort of users, if you like. It's rare for us to speak to the sort of end users of the forecast and talk about what works and what doesn't, what we could be doing differently in terms of packaging up the information we have, that sort of thing.
Very cool.
Okay, so as I suspect everybody viewing knows, the sun is a dynamic star. The sun's magnetic field observes on every time scale we can observe it. We, down to seconds, we see variability. We can observe it on millennia, and I'd love to talk to you about how we do that. It also varies on those time scales too. The day-to-day variability is what we call space weather. Changes on the sun mean changes in the near-Earth space environment, and that drives a variety of effects on the Earth. Most of the time I'm talking to people about the negative effects of space weather, and they just want it all to go away. The power companies, satellite operators, that kind of thing. It's nice to be talking about positive aspects of space weather, and that's that when you get severe space weather, you can get some really impressive aurora. So The most severe space weather is driven by coronal mass ejections. And so I thought I would just show a movie of a coronal mass ejection, set the scene. You've probably seen these things 1,000 times, but they're so pretty, it
Yeah,
bears
we
repeating.
still love them.
Yeah, exactly.
Oh,
This is the Solar Dynamics Observatory, and it's some special processing that Miroslav Druckenmüller does. It really brings out the fine detail. It's really beautiful. I'm going to press go, and you'll start to see that you can see all this little dynamic behavior, but then you see this huge eruption going off, and this is up over the North Pole of the Sun. So this coronal mass ejection is not heading towards Earth, but you can see that there's a huge volume of the solar atmosphere has been ejected out very rapidly. This is only a few minutes of observations. Most of it is able to escape the sun's gravity and flies off into the solar system. Now, when these are coming towards Earth, of course, that's when we worry about space weather. You can also see this is a false light image. And so you can see there's a real bright area here. Can you see my cursor okay? Yep.
yep, I can see it.
Cool. There's a real brightening here. That's the solar flare. So quite often, there's magnetic energy being stored up. That energy is being released. Some of that energy goes into powering this eruption that flies out into the solar system. Some of it goes into generating X-rays that give us a flare. So quite often, a big CME will give us a big flare and vice versa. But you don't have to have a big flare to get a big CME, and you don't have to have a big CME in conjunction with a big flare. So that's the kind of space weather common misconception, is that flares are driving extreme space weather, and they're not. It's the CME, but they often occur together. So after showing you that beautiful, beautiful image, I'm then going to show you a really low resolution grayscale pie chart. This is from a good colleague, Ian Richardson, who does amazing science and terrible data visualization. But this gets the point across really well. What he's done here is he's taken a few thousand geomagnetic storms and looked at what's happening in the solar wind when these storms kicked off. And you can see that when you look at the smaller storms, you get a variety of different drivers. Sometimes it's a fairly slow solar winds. Sometimes it's a fast stream that we get from a coronal hole. Talk a bit more about that in a minute. Sometimes it's a CME. But once you get up into the big storm categories, G4, G5, it's almost exclusively driven by CMEs. So that's just reinforcing the idea that the first step to forecasting severe space weather a couple of days ahead is to forecast when a CME will arrive at Earth. So then how do we go about, so we see a CME erupt, how do we go about forecasting when it will arrive? Well, we have observations of coronal mass ejections in the lower solar atmosphere. So this is LASCO data from the SOHO spacecraft. Sure, you've seen a lot of this too. But just to recap, this is white light, so just what your eye sees of the solar corona. You will know that the sun is quite bright in the visible spectrum if you've ever tried to stare at it directly, which I don't recommend. So you block out the sun with a metal disc. So this is essentially an artificial eclipse that allows you to see the fainter structures in the solar wind. So if I hit go again, this is a month of data, and it's around solar maximum, so there's tons going on. But you can see these big eruptions flying out from the sun. You can imagine if you wanted to work out how fast those things are moving, you would just take a series of images, track how far things have moved. Congratulations, you're a state-of-the-art space weather forecaster all of a sudden. That's pretty much what we do. Now, what we're looking at here, we're looking from Earth back towards the sun. So most of the structures we're seeing are not ones that are coming at us. The structures that come at us, we see as sort of halo features around the sun. I'll see if we can pick one out. There we go. I think there was one. Oh, it's moved forward. But we'll come back to this idea that you see this feature all the way around the sun when it's coming straight at us. The problem we have with space weather forecasting is that we want to know how fast these coronal mass ejections are moving. If we want to know when they're going to arrive at Earth, we need to know what direction they're headed in and how fast they're moving. Simple stuff. The problem we have is that these are big three-dimensional structures, and all we have is a 2D flat image of them. So we need to be able to reconstruct the three-dimensional features from these 2D images. And so what you have to do is make some kind of assumption about what the shape of the CME is. So a lot of the forecast agencies use something called the ice cream cone model, where you assume that your CME has like a conical shape with like a spherical dome on top. What I'm showing here on the right is what's affectionately called the croissant model. This idea that the flux rope, the CME is this curved structure. And so you can take that geometric model, just a simple shape, and you can align it in different orientations until you get it to match your available observations. If you're lucky, you have multiple viewpoints of a CME. When we had the stereo spacecraft looking back at the sun from different angles, we got multiple viewpoints, and you can do this quite well then. Typically, we've only got observations from Earth, and that makes this really hard. And so I would say the biggest barrier to being able to forecast when a CME will arrive at Earth is being able to say how fast the CME is moving and what direction it's moving in. It's that fundamental, even that fundamental information is really difficult to get hold of. So that's the first problem. And I'm sort of illustrating it, or my colleague Luke Bernard is illustrating that here. So I'll talk you through this because I think it's useful. And this is the idea that our observations are degenerate. And I don't mean they go out drinking and womanizing. What I mean there is that you can have CMEs moving with different speeds and different directions that give you identical signatures in a 2D projection, which is all we have. And that's being shown here. So in these top images, we're looking down on the North Pole of the Sun and the Earth. And you can see here there's a CME shown in purples moving out towards the Earth. Now this CME, if you compute the angle that it makes with the Sun, this is quite a narrow CME, only 30 degrees, and it's moving towards the Earth quite fast. Whereas the one on the right here, it's making a much larger angle to the Sun, but it's moving quite slow. And if we look at what we would see from Earth, we would see essentially identical signatures. So we can't, just by looking from Earth, we can't tell the difference between a narrow CME that's moving very fast or a slow CME that's moving, that's very wide. Those two signatures are identical. And so that's why we have a hard time of working out how fast CMEs are moving. Because typically we only have the one viewpoint from Earth. That's the absolute worst possible viewpoint you could pick. But, that's where we live. The other problem is that you have to do this in real time. And so you've got ratty data coming down rather than the nice, cleaned up, polished science data. So it's a really difficult thing to do. The second problem is that even if we knew perfectly which direction a CME was moving in, how fast it was moving, we've then got to deal with its propagation all the way from the Sun to the Earth. And it's not being fired into a vacuum. It's moving into a really structured medium called the solar wind, which is what I'm going to explain next. It's also frequently encountering other CMEs as well as structures in the solar wind, and that makes the propagation really complex and often quite nonlinear. So just very briefly, if you'll indulge me a second, about the solar wind. This is on the left here is a plot of temperature against height in the solar atmosphere. So we start at the photosphere, which is not really a hard surface. It's just where the density of the sun is low enough that light can escape, so it appears as the visible surface. And as you move away from the photosphere, where's my pointer gone? The temperature drops a little bit. So it starts at about 6,000 Kelvin. Temperature drops a little bit as you move away from the sun, which is good. That's what you would expect. But then it does something really bizarre. The temperature rises 2 orders of magnitude in the space of a few hundred kilometers. And if you don't think that's bizarre, you've not thought about it enough, right? It's like having a campfire, and you walk away from the campfire and the temperature increases enormously. I mean, it's really bizarre behavior. And what's happening is the sun's magnetic field is dumping heat and energy into its atmosphere, and that's causing the temperature to rise. There's a whole series of seminars just about that if you ever wanted them. Not by me, I'm not qualified to talk on that subject. But ultimately, what you've got is an atmosphere that's 1,000,000 Kelvin. That's going to be really high pressure. And off in interstellar space, far away from the sun, you've got really, really low pressure. So you've got a huge pressure gradient. And we all know what happens if you've got a pressure gradient, you get a wind. That's what drives winds on the Earth's surface. It's what drives winds in interstellar space. So ultimately, the sun's gravity cannot constrain this pressure difference between the hot, dense corona and the cold, tenuous interstellar space. And so that drives the solar wind. If you run the equations on how much the force you get from that kind of pressure difference, you get speeds that quickly become supersonic. So within maybe 10 solar radii, which is about 20th of the Sun-Earth distance, the wind is flowing away from the sun faster than any information can propagate backwards. That's the really important thing. That's what allows us to do a lot of the solar wind modeling we do, is that whatever happens in the solar wind can't ever be transmitted back to the sun. Information only flows out from the sun radially away. And so if you look at observations of the solar winds, and here, we've been doing this since the 60s, almost continuously, you see a lot of structure. That's all I want to get across with these fairly complex plots. It's just 3 consecutive months, January, February, March in 2007. I'm showing them as month plots because that's about how long it takes the sun to rotate as well. So we see the same structures coming around each month. When the sun is not evolving too quickly. This is the density, and so you see there's enormous variability in the density. You can encounter dense streams and tenuous streams. Over here is the equivalent solar wind speed, and so you see that these are of the order hundreds of kilometers a second, so millions of miles an hour. It varies between about 700 kilometers a second and about 300 kilometers a second. You can already imagine if a CME is moving in the 700 kilometers a second wind, it's going to arrive a lot faster than if it's moving in the 300 kilometer a second wind because its relative speed is so much higher. And if you've got a CME that just manages to punch from the fast wind or the slow wind into the fast wind ahead, all of a sudden that small speed difference, whether it can or can't punch into that faster wind, is going to make a big difference in how long it takes to arrive. So you've got this really structured medium. If you don't get the ambient, the background solar wind or the ambient solar wind, as we call it, right, you're not going to be able to get the CME arrival time right, even if you got the CME initial properties right, which you probably didn't. So this makes it a hard problem.
Oh boy.
Yeah, and this is the reason that because we don't get the ambient solar wind right, and we don't get the CME properties right, it means that the physics of your solar wind model are less important than the uncertainty in those conditions. And that's the sort of underlying philosophy that we're taking, that we can reduce the physics of the solar wind propagation if we can better quantify the uncertainty in those initial conditions. So this is the sort of state-of-the-art way that we do this, and we've been doing something similar for about 20 years now. We can observe the magnetic field at the solar surface. You can use that to model the corona, and the corona has tons of complex, interesting physics in it, and so you need the complex physics-based models really to do that well, although there are approximations that work reasonably well too. But you use your complex model to solve the sort of minimum volume that you need to, because those models are expensive. So you typically solve for the coronal physics out to about 1/10 of the Sun-Earth distance. So 21.5 solar radii for those interested. Then you hand it off to the solar wind model, and the solar wind model then runs it out from 1/10 of the Sun-Earth distance to Earth orbit. And then if you're feeling adventurous, maybe you drive a model of the Earth's magnetosphere with it. But that's typically not done operationally. You sort of forecast the solar wind conditions near Earth and draw your conclusions from that typically. The kind of models that are used for this, so SWIPSI and the UK Met Office are using a model called ENLIL. There are quite a few of these kind of models. The physics they're solving, they're three-dimensional numerical simulations. They're solving something called magnetohydrodynamics, which is basically just fluid dynamics, but with a magnetized fluid. So it contains a magnetic field too. It's fairly computationally intensive, but it is the right physics to use for the solar wind. It is a fluid flow. This system, though, won't get you any coronal mass ejections. So the coronal models don't naturally produce eruptions. And so you have to somehow stick your coronal mass ejections in artificially. So this is the real way that the operational forecasting is done, is that you have photospheric magnetic field observations and coronal models that give you the background solar wind. And then you take your coronagraph observations, you fit them with some geometric model to get the CME direction and width and speed, and then you stick in a lump of material that has those same properties into your solar wind model, and that approximates the CME and maybe gives you an idea of when it will arrive at Earth. So it's pretty coarse stuff, I would say, but it's the best we can do with the observations we have. So here's a movie put together by Dujon Ostrasil. He's the developer of the Enlil model. And this image is 20 years old, but still entirely valid. This is the solar wind model domain. And so this is the inner boundary for the solar wind model here is this pink and blue and green sphere. That's the solar wind speed from the coronal model. You see, it's not changing with time. It's being held constant but rotated. So you take a single coronal run and you use that for the 5 days that you run your solar wind model. And then on top of that, that gives you the nice spiral structure. On top of that, then you put in this perturbation that approximates a CME, and you try and work out when that's likely to hit Earth. So there we go. It's just hitting Earth there. That's what pretty much every forecast agency is doing. That's what we're doing too. We're just doing it more often, as I'll show you. Now, how well does this work? And this is the sort of open secret in the field, is that it's not very good. It's as good as we can do. Pete Riley put together a really nice summary of the results of genuine forecasts, so not hindcasts where you can tune them to the answer you want. These were genuine forecasts put out before the event, and then he looked at how well they did. There are different forecast groups on here. NOAA SWIPSI, the UK Met Office, Goddard. Basically, the width of that distribution tells you what the average error is, and they're all around 20-ish hours. So plus or minus 10 hours is fairly typical. Don't look at this plot and think, oh, NOAA SWIPSI has the lowest error, therefore they're the best forecasters. Hooray, I'll just look at them. It's not they're not all forecasting the same events here. This is just to give a general idea of the sort of errors involved with this sort of forecasting. They're all using the same inputs. They're all using broadly the same models. They're all getting broadly the same kind of uncertainties. And that is that a CME takes 2 to 3 days to arrive at Earth, and that the uncertainty is of the order a day, or plus or minus half a day. So it's a fairly considerable uncertainty. I don't think anything I do can significantly reduce that error. The error is inherent to the observations we have. We just don't have good enough observations to really do dramatically better than this. Some models are better than others. There are tweaks. What we can do, however, is quantify the uncertainty better. Not each of these CMEs was equal. Some of them, the uncertainty was going to be large. Some of them, the uncertainty in the forecast was going to be small. Sometimes you'll get a CME that's right on the fast slow boundary. And so if it's just below 700 kilometers a second, it's stuck in the slow wind and it's going to take ages to get to Earth. But if it gets just above 700 kilometers a second, it might punch into that fast wind and its arrival time will come down dramatically. And so small changes in the initial conditions sometimes can give you big changes in the arrival times. And we can work that out. We can quantify that case by case uncertainty. It's not every CME, the uncertainty is plus or minus 12 hours. For some CMEs, the uncertainty is plus or minus 5, 6 hours. For some, it's plus or minus 24 hours. And we can quantify that better. I think that's the step we can make an improvement in. So this is the idea of doing ensemble forecasting. So ensemble is an alternative to a deterministic forecast. So a deterministic forecast is what a lot of the forecast agencies are doing, which is you take your best estimate of the ambient solar wind, your best estimate of CME parameters, you put them into your best model, and you run it forwards and you say, okay, this CME is arriving at 7:32 and 15 seconds on Tuesday evening. And that's it. There's no range of uncertainty. There's no confidence in that forecast of whether it is a good or a good forecast. There's no even probability of will it, won't it hit. It's just a yes or a no, 100%, 0% probability, and an extremely accurate arrival time. Whereas the probabilistic approach that you get from ensemble forecasting is you say, well, okay, we determined that CME speed to be 750 kilometers a second, but let's say maybe it's 700, maybe it's 800. How much does that change our forecast? And you could run 1,000 different simulations with slightly different parameters. And quite often your best estimate will not change at all from your deterministic run, from your single run. And the reason is that you're perturbing your parameters around that best estimate. And so often, this isn't ensemble forecasting is not necessarily about improving your best estimate. It's about quantifying how confident you are in it. If you change things about a little bit and it doesn't really change the arrival time, you can be confident. If you change things a little bit and it massively changes the arrival time, you should not have confidence in that forecast. And that is a really useful thing to quantify. And the Met Office, the UK Met Office, is doing some of this and has been for a while. The problem is that at present they can't explore that uncertainty as well as they would like. So at present, every UK Met Office forecast, they determine the CME properties and then they perturb them slightly and do 24 different runs. Now, I would argue and they would argue that that's not sufficient, because you've got CME speed, you've got the time at the inner boundary, you've got the CME latitude, the CME longitude, the CME width. So you've got 5 parameters just for the CME. If you want to look at 10 values in each of those, you need 10 to the 5 runs to look at all the permutations. There are clever things you can do to reduce that number, but still, you need of the order of thousands, not of the order of tens. And that's just not possible with 3D MHD. You can throw more resource at the problem and you can go from 24 ensemble members to maybe 100, but that's not really enough. If you want to fully explore parameter space, you need a slightly different approach, which is that's the angle we're coming at. And just to persuade you that I'm about to show you a model for the solar wind that makes some really gross approximations. And as a solar wind physicist, I am somewhat uncomfortable with them myself. But A, it works. I'll show you the comparison with 3D MHD. And B, there's a fairly good theoretical underpinning for why it should be an okay thing to do. All approximations are bad, but some approximations are better than others. If you take typical properties for the solar wind, you can work out roughly how much energy is contained in the flow of the solar wind, how much energy is contained in the thermal motions of the solar wind, and how much energy is contained in the magnetic field of the solar wind. And if you plug those numbers in and do a really crude back of the envelope calculation, the energy in the flow of the solar wind is 2 orders of magnitude higher than the energy in the magnetic field. That says, to first approximation, ignoring the magnetic field is not a bad thing to do. I mean, ideally, you would want to include it, but ideally, you'd want to get the inner boundary conditions right too. And tough, you can't. And so I think it's better to fully acknowledge that the inner boundary conditions are uncertain and ignore the magnetic field than it is to assume the inner boundary conditions are okay and include the magnetic field. So we have this model, HUXt, for want of a better name, but it's a one-dimensional model, and I haven't really gone into the justification for why you can treat the solar wind as one-dimensional. But anyone who's looked at any solar wind data will tell you that the flow is almost entirely radial. The non-radial flows are very small. And there's also some other physical arguments that I can get into, but I'm glossing over here. But it's one-dimensional and it's hydrodynamic. So there is a magnetic field, but it doesn't affect the flow. And this, we get solutions that look like Enlil, they look like Euphoria, they look like 3D MHD. This is not a 2D solution here. This is a series of one-dimensional solutions all just sat next to each other. So one longitude is not talking to the next longitude at all. You can just simulate one longitude if you like. And in fact, that's what we do a lot of the time. That allows us to really beat down the computation time. So Enlil, for example, might take 5-6 hours to run on 100 CPUs. This takes about 1/100th of a second to run on one CPU. So, this isn't about reducing computation a little bit. We're talking orders and orders of magnitude difference here. And that's what enables you to do something different with it. Even though it is cruder, Enlil's the better model, Euphoria is a better model, but you can do things with this that you couldn't do otherwise. If you want to grab, it's open source as well. If anybody wants to grab it and play with it, it's pretty easy to use. Just to show you that it approximates 3D MHD quite well, here is, we're looking now down on the ecliptic plane. You can see this classic Parker spiral structure. This is the solution from a really sophisticated 3D MHD from the predictive science group called Heliomass. There's their solution. If we take the exact same boundary conditions and plug them into HUXt, we get this. You can see, to first glance, they're very, very similar. If you compute, that's it, computing the difference. We did this for 40 years of observations. So they do a new solution every month for 40 years. We ran all of them, 700 or so different solutions. These were the 3 absolute worst out of 700. The red is HUXt, the black is 3D MHD. So there is some difference in these ones because these are the absolute worst of the bunch, but it's still pretty close. If you're just interested in where's their fast wind, where's the slow wind, it's doing a pretty good job. And let's be honest, 3D MHD is not right either. It itself is an approximation.
Yeah, it's pretty impressive, really.
Yeah, for a cheap, given the level of approximation that goes into it, it surprises me it works as well as it does. You can do the same for CMEs. So here's a CME at 3 different times in a 3D MHD model. Here's the same CME in the same solar wind from HUXt. And you can see, there are sharper gradients. Features are not identical, but they're very, very similar. And again, the MHD is not right, but that's what we're attempting to emulate here. So we use this for forecasting. So if you go to this website here, assuming a cleaner has not turned off the box that it's running on, you'll get this forecast. This was 6 a.m. this morning, which is when I wrote this talk. This is the standard forecast, if you like. We take gong magnetograms, so that's the particular observatory that we use for the photosphere. The UK Met Office runs the Wang-Shili ambient solar wind model for those of you that are interested in this sort of stuff. And then Met Office observers look at the coronagraph observations and try and work out direction and speed of CMEs. We put all those things together and chuck them into HUXt, and this was the forecast for this morning. So you can see a few CMEs going off there. Those are the coloured lines, if that wasn't obvious. Nothing headed towards Earth for the next 5 days from this. So at the moment, 2-3 days ahead, we would be predicting not much in the way of space weather. Now, the point is that here I'm using it as a deterministic run again, but that's not the limit to how we use this thing. So just to reiterate why we're throwing away all that good physics, we can get as soon as we get a new set of observations, we can get a forecast within a second. There is use even with 100 CPU cluster, you're still waiting 4 or 5 hours typically for an NLO run. So you get that instant forecast, which can be useful in some circumstances. But the big thing is that we're going to run it in big ensembles and quantify the uncertainty. The code's really simple. It makes it really easy to integrate into other things. If you want to integrate this into a DST forecast, it's very simple to do. It also enables us to write what's called an adjoint model, where we essentially rewrite the model equation or invert the model equations so we can run it backwards in time. And that enables us to do some data assimilation techniques, which is weather forecasting is as good as it is today because of data assimilation. And we're trying to bring some of that into space weather. But that's another talk in itself. It's also a really robust code. As I say, our forecast is frequently not available, but that's not because the code falls over. That's because the janitor has unplugged it or whatever. You can throw whatever inner boundary conditions you want at HUXt, and it will give you a solution. It's kind of bomb-proof. So there's some resilience in that, and it makes using different inputs from different coronal models very easy, which I'll show here. And this image may give you pause for thought when I explain what it is. So this is the HUXt solar wind in the ecliptic plane. So the blue dot is Earth, the black dot is Mercury, this is Venus, and these are the stereo spacecraft. So you're looking down on the North Pole again. This is the typical forecast we produce, which is where the inner boundary is set by this WSA model with the Gong observatory. The details are kind of not important. This is the exact same observatory, but a slightly different model. And you can see already that's changing the stream structure a bit and how fast some of these streams are and things like that. This is the exact same time period, but with a different observatory and a different model. This is the exact same time period, but using coronal tomography, where you actually take white light observations of the corona and not an photospheric observatory and try and work out the solar wind. So HUXt will happily run with each of these, and for this coronal tomography one, we had to put the inner boundary down at 8 solar radii, which 3D MHD model would not be happy with that because it's below the sonic point and waves can propagate at the boundary and make it numerically unstable. HUXt doesn't care. That's one advantage of being dumb, is that it'll just run with it. But these are supposed to be the same solar wind at the same time, and they're really different. And so what I'd really like for the future is to be able to use as many different coronal inputs to sort of assess the uncertainty in the ambient solar wind. We're building a lot of the machinery to do that now. When we just have one input, so typically we have this WSA Gong one, we can still get some estimate of the uncertainty in that forecast. So this is a bit of a confusing plot, but and I blame my student Nathaniel for this. He put it together. It's really nice. Here's here's the inner boundary for our model. This is a sphere at 0.1 AU, so close to the sun, and the colors are solar wind speed. And what we do is instead of just taking that inner boundary condition as it is, we say, well, what if we tip it this way a bit, or what if we tip it that way a bit, or this way a bit? How much would that change the forecast of the solar wind, and how much would it change the forecast for CME arrivals? And so we look at the sensitivity of our forecast to slightly perturbing what the coronal models tell us the solar wind is, because we don't trust them, and you shouldn't. And so, for a given, here's a map. So this is latitude, longitude. So we've taken that sphere and unwound it. So this is a Mercator projection. This is at 0.1 AU. Earth at this time is below the equator, so that's the red line there. What we would normally do is just take the solar wind along that cut there, use that to drive HUXt, and this is what we would get at 1 AU. This is what we would get at Earth, sorry. We'd get this time series over the next 27 days of what the solar wind does at 1 AU. But what we now do is perturb that, and I'm only showing 100 perturbations here. We typically do a few hundreds, maybe 1,000 of these. And this gives us a kind of time-dependent uncertainty in the ambient solar wind. There are times where, from the model, we're confident we're going to get fast wind, whereas here, this time here, we can see it spans the range from below 400 to up to 700, and so we're uncertain at that time. And that time-dependent uncertainty is a useful thing. If we were going to put a CME into this portion of the solar wind, we might be fairly confident in its arrival time. If we're going to put a CME into this portion of the solar wind, we're going to be less confident. And so that's one of the forecast products. So this is a really nasty, complex plot, and I apologize for that. It's mainly my doing, so I have to bear the full brunt of responsibility. But what you're seeing here, I'll talk you through it. Here is the current time. So the gray shaded region is the past, the white is the future, and we're looking sort of 7 days into the future and 5-ish days into the past, I think. This forecast was at 6 a.m. this morning, so you can see it's partway through the 19th there. The red line on here is the real-time Discover data. This is solar wind speed. Now, the model should match that, and it doesn't. And there are two reasons why it doesn't. The one is the obvious one. The model is wrong, and it is. The second one is that the Discover real-time data is wrong, and it is. Getting real-time spacecraft data down is difficult. You have to do all the processing on board the spacecraft. You have to downlink it quickly. We're used to looking at nice science data that's been processed a month after it was taken. The real-time data is often full of nasty artifacts. And so it can be wrong by easily 100 kilometers a second. That's what you have to deal with forecasting, though. This region here shows our forecast of solar wind speed into the future, and so you can see, it's forecast to ramp up over the course of the day. I don't think this actually happened. I haven't looked, but you can see that we were quite uncertain as to when that solar wind speed rise would occur. There's an error on that. There is more than a day. The different colored regions are the different confidence intervals. So this tells you what fraction of the model runs predicted a certain solar wind speed at a certain time. As you move out, you've got less and less confidence, if you like. And then we look at putting CMEs into this. And for this one, there were no real Earth-directed CMEs, and so it's not a very useful example. So I'm going to go back to an old forecast. And what I'm showing you are genuine forecasts, but they are from past. So let's go back to an event we probably all know, which was the CMEs that erupted on the 8th of May and then arrived late on the 10th of May. So on the 8th of May at noon, we'd only seen one CME coming towards the Earth, but we were pretty confident something was going to go on, and we put a forecast out on Twitter, which we don't do very often, just to say, "Hey up, there's a fast Earth-directed CME coming this way. We're very confident it's going to hit." And so this was the forecast from the time. So there'd been this glancing blow earlier on the 5th. And then there was a big Earth-directed CME that's about to erupt. There we go. And it was nice and fast. And it arrived. Oh, I can't pause it. Apparently, it arrives sometime late on the 10th, early on the 11th. And so the forecast dashboard for that looks like something like this. So again, here's the time that the forecast was made. And we were forecasting that in sort of 2.5 days' time, a CME would arrive at Earth. So we take all of the Met Office Observer CME properties, and they're plotted over here on this really, let's see if I can get it up, this really messy image here. The background is the solar wind speed from the WSA model, and each of these circles is a CME. So this is where the Met Office predicted it was headed, and it's got the correct width. The grey ones are the ones that we say have no chance of hitting Earth. The coloured ones are the ones that we thought have some chance of hitting Earth, because we perturb their directions a little bit, and so we give a percentage chance that they will hit Earth. The big one that we saw was this cyan color here. It's smack around Earth, which is the dot here. And so that was CME 14 in this time period. We gave it a 99% probability of hitting Earth because it was clearly coming straight at us. What we do though is we track. I think in this run there was 500 runs, and so we say what percentage of runs had that CME arrive in a particular window. And so instead of getting a single arrival time now, we get a distribution of arrival times. That's what this ensemble density plot here is. This is essentially probability of the CME arriving. And so you can see for some CMEs, this red one here, it can be really broad. Whereas for this CME, it was actually quite narrow. And we said from maybe sort of midday-ish on the 10th to maybe midday-ish on the 11th. So it was, but most probable value at this time, because we'd only seen one, was early hours of the 11th. I'll go into a bit more detail about that in a second, but let's just look at what actually happens. So there was that one CME that came towards the Earth, but then it was rapidly followed by a whole host, maybe 7 or 8 others.
Yeah, this is fun to watch.
Yeah, and I'd never seen anything like this, and it broke our dashboard because we had too many CMEs to track and all this kind of stuff. But those faster CMEs behind were pushing into it, and so that interaction was really important for the shock arrival time at Earth. You can't just study the one CME in isolation, which some of the modeling approaches do. You need to consider everything that's going on. So that's what it looked like on the Friday morning. Now you can see we're tracking a whole bunch of CMEs coming at Earth. We've run out of colors. Our graphics are overlapping each other. But you can see that there's still quite a narrow distribution of arrival times. So we were confident when this CME would arrive. We said we had it, most likely time was around, let's see, which ones is it? Some of these in here. Most likely time was around 10 p.m. on the 10th, but the error on that was plus or minus 6-ish hours. And that error is a 1 sigma error. So that's a sort of 66% confidence interval, which wasn't bad actually. But you can see not all the CMEs in that interval are the same. You look at this green one here, the arrival time estimate for that one is very, very uncertain, because this CME, what was happening is if it was just fast enough, it was catching up with the fast CMEs ahead of it and essentially drafting behind them and arriving very, very quick. But if it was just a little bit slower, it wasn't able to do that drafting effect, and it was taking much longer to arrive. And so we knew that these arrival times were fairly well constrained. We knew that these arrival times were very uncertain. And I think it's that kind of, we're not necessarily, I'm not saying that our forecast of arrival time was better than the forecast agencies, but I think our assessment of the uncertainty in the forecasted arrival time was better, because we can sample that parameter space. And when you've got 10 interacting CMEs, you really, really need a large parameter space, because you've got to perturb every CME a little bit and look at all the different permutations of those. In fact, our 500 runs that we did for this probably wasn't enough. And I mean, the 500 runs takes a minute. We probably should be doing 10,000. There's no reason not to, really. But in most circumstances, 500 is enough. When you've got 10 interacting CMEs, that's when we probably should be automatically increasing that number. Okay, how am I doing for time, Mary Beth?
Oh, you're fine. You're absolutely
Okay.
fine. Like technically it's like 10 more minutes, but if it goes over, it's fine. So
I won't go over. I respect people's time too much for that. Um, I will just very, very quickly then summarize some of the future developments. So I've got a student at the moment, Nathaniel. He's working on ensemble calibration. So at the moment, we say, okay, the CME speed is 700 kilometers a second. We're going to perturb that by, on average, 20%. And that number is plucked out of the air for no good reason. What we really want is that when 60% of our ensemble members are predicting a CME will hit, we want to be right 60% of the time. That's a process called calibration. It requires you to do a huge amount of runs. So you tweak your perturbations until you get your number of ensemble members matching your forecast probability. It's very difficult to do with 3D MHD. It's quite easy to do with a cheap model like HUXt. So we're doing that at present. I really want to do multi-model ensembles. This is where we take all the different sources of information, all the different coronal models, all the different estimates of CME parameters, and you fold them all in together to give you, instead of saying, here's our WSA gong forecast, and here's our Dumfrick HMI forecast, and here's our coronal tomography forecast, is to bring those all together and fold in all the uncertainties. And we've got a lot of the machinery in place for that, but it's hard to do right. The one area where I think we might actually improve forecasting, or no, I'm going to go better than that. The one area where we will improve forecasting, I think, is data assimilation. I still stuck a think in there, didn't I? I can't help but caveat myself. This is where you take the available observations and you use them to nudge your forecast back towards reality. At the moment, we set our models running at 0.1 AU, 10th of the Sun-Earth distance, and then we just leave them free running from that point on. We don't put any further observational constraints on them. And we have observations of the solar wind that we can use to nudge our models back towards reality. And that's what they do in weather forecasting, and that's what we're doing with that, with these solar wind models. And it definitely helps. I really want to do time-dependent solar wind modeling. I'll just show a very quick image of that. I think what we really need to do is package up what we're doing a bit better. If anybody listening wants to contact me after this with ideas of how we could do that, I'd love to hear from them. I have a summer student working on, or sorry, a project student working on this at the moment. I'm not going to go through uncertainty quantification. I'm not going to go through DA. I will just quickly flash this up in that Luc Bernard is working on using heliospheric imager. This is actual images of the solar wind, sometimes all the way out to Earth, how you can use observations of CMEs in that to nudge the model back towards reality. It's really promising. I really want to move away from how we currently do solar wind forecasting, and that's that, we run the model today, we get a new solar wind solution tomorrow, we throw away our solution from today and throw away all that useful information and just start a new model run the next day. And so that causes your forecast to jump about a lot. So here's the steady state approach. This is just 1 month. Each day you start a new run, you throw away the old one. What you really should be doing is just continually updating your inner boundary, and you get a much more physically realistic solution. But I'm really glossing over the details now. The point was, solar wind, if you want to forecast severe space weather a couple of days ahead, you've got to forecast when a CME arrives. It's hard because we don't know what the CME properties are, and we don't really know what the solar wind that CME is propagating into either. So instead of concentrating on making your solar wind model as sophisticated as possible, I think there's value in investigating the uncertainty in your driving conditions. So we use HUXt for this. It gives us a very rapid forecast. It gives us this estimate of uncertainty. It's starting to enable us to do data assimilation and time-dependent simulations. I mean, that because it's a really easy to work with model and you get an instant result, it makes us, I think the software term is agile. We can try things quickly, and if they don't work, we can throw them away and move on to something else. Whereas it's very difficult to do when you have to burn a lot of computation. So I'd really like to know from those listening, what developments would you most like to see? What would be most useful? Obviously, you want more accurate forecasts, and we're trying on that. But that's the hard thing to deliver. Are there easy things we could do that would help you?
Yeah, I mean, yeah, you nailed the obvious one is the accuracy because, well,
Yep.
like some of us living in the light polluted areas that I live in, having to plan a drive, a 7 hour drive, it's like, but
Yeah.
um yeah,
And for you, the false alarms are almost worse than the missed events in that case,
yeah,
right?
they really are. I've learned to just be like, more accepting of it, but it's just kind of funny.
Yeah.
Um but yeah, it's no, what is interesting, actually, what I appreciated you talking a lot about here is what the solar wind actually is and how you use, because like I don't think I've ever really had a good explanation of like the temperature part of it and that pressure difference and how that really, really makes a difference and when you're running models and things like that. So that was cool to get insight on. And let's see, Tanya says, will multi-point observations help reduce uncertainty? Which I think my intuitive answer is yes. Like if we had different satellites looking in from different angles.
Yeah. There's two kinds of multi-point observations as well. One is if you've got two that are sort of remote sensing of the corona, so you see a CME from multiple viewpoints. That really helps with determining the CME properties. But also, if you're directly measuring the solar wind in situ, like weather stations, essentially at multiple points, that really helps with the data assimilation.
Yeah, I
So
think that would be cool too to like you said, working backwards. Like we get like an event like May and then seeing how well the model worked too. Yeah, I think that's really cool. I'm trying to think of anything else like so as aurora chasers, I guess one of the questions I have, even though I know you said you ignore the magnetic component of it, because we're always like, is that going to have a southern
yep,
pointing BZ?
I glossed over all of that. So yeah, the the first thing you have to know is if and when a CME will arrive, but that's a necessary but not sufficient criteria for good aurora, right?
Right.
You then need the field to be southward. And at present, I would say we have no ability to forecast that other than tossing a coin.
Right. And I think that's our main $1 million question is getting to that point where we can, you know, sort of forecast that. I guess there's like some ways, people looked at, but again, it's like off of the solar disk. Like you can, pick up, how it's launched, but is that the way it's going to arrive?
Yeah.
Probably, probably not. So yeah, it's like that always
And
that makes
there are a few studies that have shown some relationship between the sort of filament orientation on the sun and BZ, but I've not seen any of those applied to forecasting. And the
yeah,
one thing I've learned is that doing a bunch of hindcasting, even with the most disciplined ethical approach you can come up with, that you're not trying to get towards a specific answer. It, your capability really changes when you're using real-time data to make a genuine forecast. It is a very, very different ball game.
right. But
And
no,
I
this
don't think a lot of space physicists who are working with science data truly appreciate that.
right. So, but that's the main ones I have, unless Connie wants to pop in and ask a few questions. I know she's usually better at I'm bad at like coming up with stuff off the top of my head. I'll think of it later and then I'll just email you like, hey, I thought of
Sure.
something. But yeah, it's like but I think what you're doing has a lot of merit and and I like the direction it's going to because like being able to do this faster than real time and really quickly and trying different things I think is really important. Um
Yeah, and the aim here is never to replace the 3D MHD modeling.
yeah,
It's really useful, and ultimately, one day we might be able to include CME magnetic fields realistically in
right.
those kinds of models, and that will be great. But I think there'll still be a place for this fast, simple modeling because it allows you to estimate, search parameter space and figure out, well, what kind of runs do we want to do with the expensive codes?
Yeah. Like the ones that would make more sense for because from the operational standpoint, I mean, there's obviously assets that have to be protected. So like, that's the important where we get the fun part of it of just watching the pretty stuff that happens, but there's actually, really important things that need to be addressed.
Yeah. And there it's quite the opposite situation. Quite often is that for a lot of the infrastructure protection, the missing a big event is the real thing that you don't want to do.
Right.
So
Yeah.
you can tolerate false alarms so long as you don't miss events. Whereas for aurora hunting or chasing, it's probably more that you're willing to miss one or two so long as you don't have tons of false alarms and
Right.
waste the time. There's a
Exactly.
different risk tolerance there.
Yeah, that's for sure. Alrighty.
One thing I'm going to pop in and I'm just going to say one thing that what is really not appreciated and maybe not communicated in official for space weather forecasts, although Met Office is doing a pretty good job, is a forecast uncertainty. Even knowing sort of a spread when CME might arrive based on a prediction would be really helpful. And the probability of of the arrival is definitely huge. And I know there are limits to what can be done with the probability of arrival too, because some
Yeah,
of them may be sort of moderate confidence in arrival, and it may not show up. And what we see from the recent study, so there was an update to 2018 study of forecasting accuracy. It's still about the same. It hasn't improved, and about 1/3 of predicted arrivals are actually misses. So it's great for industry, and not so great for our chasing. But
yeah,
appreciating that uncertainty, and this is where HUXt really comes in, that this is high confidence in arrival versus lower confidence in arrival, kind of allows us to make decisions to some degree. Are we going to sit it out and wait when it happens, or are we actually going to be prepared for something to hit? Knowing full in advance that it may not be the same geomagnetic storming as forecasts are predicting.
yeah. I mean, the only thing I worry about a little bit with the way we currently use HUXt is that there's a lack of diversity of inputs in that, we've got one forecaster who's fit the CMEs, and it's a really difficult thing to do. Um, what we really need is multiple people that are doing these CME fits, and that we take all of that information, and when they're all in agreement, we can be confident. But when they're all disagreeing slightly, and we need them to be truly independent, when they're all disagreeing slightly, then we have less confidence in those CME parameters, and maybe we want to make our ensemble spread even bigger in that case. Because at the moment, I think we're looking at certain aspects of uncertainty, but we're underestimating the complete uncertainty. There have been times where we forecast a CME will hit, with 95% confidence, and it's not shown up. And that's because we're reliant on one individual to estimate the CME direction. And it's hard.
That's a good point too. Yeah. Yeah, it is. I, I appreciate everything you guys are doing because it is very difficult when you're very limited on what you have to work with.
Yeah.
So the fact that we have anything at all, it's just like I try to, to keep people like happy about it. It's like, hey, 20 years ago, like people used to like Aurora was a thing that you just by chance saw and it was rare.
Right.
And then now we actually do have, especially with like events like May, I don't know, a couple days heads up.
Yeah.
And
Yeah.
that's
Yeah.
that's pretty huge, even with the limited
And
amount of data.
to within a few hours, 2.5 days ahead. I mean,
Yeah.
that I think that is one of the success stories. I mean, maybe we got there more through luck than judgment, but still, occasionally we get it right.
Yeah, so it's all good.
We got a couple of questions from the chat. So
Okay.
first question, what actually causes the delay in the HUXt being up for the public? And does it get revised midday if new parameters get included?
So at the moment, we're reliant on the Met Office making their WSA results and their co-models available for architectural reasons that I find incredibly frustrating. But that's the way that the system is built. We tend not to get those until after NLIL has run, which doesn't really make any sense because we could do something with them 4 or 5 hours ahead. Um, that's just one of those things. I think we may get around that in the future. I also want to start routinely running. We have a homebrew version of WSA that we can run with, that's fully open source, so we can make that available to everybody, which I
Oh,
think is
cool.
useful. But in the M2M office, through the Donkey CME database, we could start running with their observations too. I've done that occasionally for a couple of events just to look at uncertainty, but there's no reason why we couldn't be doing that
Uh-huh.
routinely. And we
And
should do that. We should do that anyway because that
Yeah.
is an independent estimate. Yeah, that's
and
on.
yeah, so M2M model does run several IMF clock angles, and that allows to estimate the KP as much as we do not recommend using KP forecasts or real time, which is not really real time for aurora chasing. But is there a way to include it, or is it going to be computationally demanding? And is there a reason to do it in the first place, given that right now our ability to predict the IMF polarity is slim to none?
Yeah,
It's important for industry to estimate what's the worst possible case scenario would be. That's why it's run for like 180 degrees clock angle.
right. Yeah, we could do a worst case scenario thing. And we have some estimate of solar wind speed, which factors into some of the way in which the solar wind couples to the magnetosphere and gives geomagnetic activity. We've been looking into, could we say something probabilistic about geomagnetic indices? So, we from the solar wind speed, we can very crudely estimate the magnetic field magnitude. So faster CMEs tend to have stronger magnetic fields. If we then say, well, there's a 30% probability it will be a southern field. 30% northward, 30% in the ecliptic, 30% southern. We could then probabilistically say something about different geomagnetic field thresholds, maybe. But I don't know how useful that is, because you're putting in an even weighting for the magnetic field.
Right.
And it's not
Yep.
it's not on an event by event basis either. You're treating every event the same.
I think we have to wait for IMF polarity to appear at L1 and just run with it.
Yep,
Yep.
that's my sense.
Oh well.
Yep. Back to L1.
Yeah. Well, sweet. All right. Did we have anything else?
Nope. That is it for questions.
All right.
Cool.
Well, sweet. Well, that was awesome though. Thank you so much.
It's nice to meet you both.
Yeah, I know. It was
Thank you.
some of this, like, what the fun part about doing this is actually, being able to meet, like, all these scientists that work in the field that we, I joke with Tanya a lot because some people have like this thing for celebrities, but we have things for scientists that
Oh
work
God,
that work in the field. And it's like, oh, it's like meeting celebrities. It's awesome.
just
So,
less dynamic.
but we like it. We enjoy it. And I always learn something, especially, the people that are behind these things, and you get to learn a little bit more of the inner workings and how they come up with the stuff. So no, we really appreciate it. So thank you.
Cool. It's been great to chat.
Yeah, but I will end this on the YouTube and then we'll just say our goodbyes. So thank you again.